Hi there, Frank here, as always. Today we're going to talk about the Boucherot theorem. Let me just get rid of those pen. I'm going to use them later. So we're going to talk about the Boucherot theorem. What the Boucherot theorem says is that the real power, the active real power absorbed by a complex circuit corresponds always corresponds to the arithmetic sum of the individual active power dissipated by each individual resistor. So if I had to write it down, I would say that the real active power absorbed by a complex circuit corresponds to the algebraic sum responds to the algebraic sum of the individual active powers dissipated by every individual resistor. So the real active power absorbed by a complex circuit corresponds to the algebraic sum of the individual active powers dissipated by every individual resistor. So if I had to make circuit as an example, I will say, well, I will do something like this. With a resistor here, which I'm going to call R1, and an inductor, which I'm going to use later. And then I will have a resistor here and a capacitor, which I'm going to use later. I'm going to tell you why. And another resistor here, another inductor here. I'm going to call this R3 and this one R2, this one X3 and this one X2. And then I'm going to connect everything down all the way to here. I have V and V. Okay. So if I had to write this, I would say, well, I will have sometimes, well, in books you will generally find an angle divided like this, like so. In which this angle is phi, this one is Q1, this one is P2, 2, not 3, this one is Q2, this one is PT, this one is QT, this one is Q3, this one is P3. Now, if I had to write this as a formula, I would say that the total power will be equivalent to the power of the resistor 1 plus the power dissipated in the resistor 2 plus the power dissipated in the resistor 3, etc., etc. So this will be my formula. And it's actually pretty straightforward because this is a result well, this result here is basically a consequence of the conservation of energy. For the reactive powers, though, there is, well, something similar, but except for the inductive and capacitive circuits, in which there are inductors and capacitors, in which there is a sort of compensation action between the reactive powers. So the reactive power, the total reactive power, is basically the algebraic sum of the single reactive powers that come into play in each inductor and capacitor. So I could just say that this is just say this follows from the conservation of energy. And then I also want to point out about the reactive power. So for the reactive powers, there is something similar, except for the inductive and capacitive circuits, where, well, in which there is a sort of compensation action, a sort of compensation between the reactive powers, the total reactive power, oh, this is a power, is the algebraic sum of the individual reactive powers that come into play in each inductor and capacitor. So if I had to write it as a formula, I would write it as Qt equal to Qx1 minus Qx2 plus minus the other. And this will be my other formula. Because there is this kind of compensation, as I said. Now, this basically means that in the same circuit, we can find couple an inductor and a capacitor, and there is, well, what happens is that the magnetic field that is formed across the inductant, when the current goes up, gets the energy from the electric field of the capacitor, and then when the voltage at the capacitor is going up across the two part of the capacitor basically is going up. Well, let me just, let's say that you have an inductor. Oh, come on. Well, no, that's not the best of the drawing. But let's just say that you have an inductor and you have a capacitor. Okay. So basically what happens is that if you have both of them, when you basically have but you have both of them in the same circuit, the magnetic field that is across the inductor, when the current goes up, gets the energy which is freed from the electric field of the capacitor. But then when the voltage at the at those two ends of the capacitor is going up and the current is going down, then the one that is actually giving the energy is like the one that plays the role of giving the energy is going to be the magnetic field in the inductor that is going to be dissipated bit by bit. So in this way, you have a sort of exchange between the two components, and you have an exchange between the magnetic field and the electric field, so that the power supply that we'll have somewhere here is only just has to give and get from time to time the difference between the energy that is stored between those two ones, between those magnetic and electric fields, which basically means that the reactive power of the whole circuit is just the difference or the algebraic sum between the reactive powers, the inductive one and the capacitive one. And lastly, as the last thing that I want to say is that the apparent power is the vector sum of each and every individual power. I can define it as well. I just write it. I just for the sake I've been writing about those two, so I'm gonna write this as well. Well, what can I say? Yeah, I can just say the apparent power is the vector sum of the individual apparent powers. So if I had to write it as a formula, just like the other two, I will write it as ST equal to, well, the vector sum. What's the vector sum? Is like the norm. So, sorry, PT squared, of course, plus QT squared. And this will be my last formula for the Boucherot theorem. So yeah, this is basically what the Boucherot theorem says. Memorize this as you're gonna be using this. Well, we have already been using this like in a sort of implicit way, because everybody uses the Boucherot theorem, but they just many people just don't know that it's actually called, the reason why you're using that is that it's called the Boucherot theorem. But many people just use it and completely ignore what that is and where it's coming from. So yeah, that's pretty much it for the Boucherot theorem. Goodbye.